In this video, we will carry on with our consideration of models of the atom, and we'll start off by talking about the Rutherford model of the atom and talking about the issues that are found with that kind of classical model of the atom. And that really opens the door and opens the need for quantum physics. And so at the same time, we'll also be considering how the whole idea of quantum numbers and packets of energy came about. And so we'll be focusing on that in this video. But first of all then, let's take a look at the Rutherford model of the atom. Remember that he aimed, along with Geiger and Marsden, he aimed alpha particles at a gold foil and noticed that they scattered by massive angles, and that suggested that the positive charge of the gold atoms was all contained within some small nucleus, and that the rest was largely empty space. And so the alpha particles would come in, many of them would pass straight through, but about 1 in 10,000 would backscatter by a huge angle, and that's best explained by this very compact, densely concentrated positive charge that is the nucleus of the atom. And so Rutherford saw this very much as an analogy to the planets in the solar system orbiting the sun. So the atomic model so far then, for the case of the hydrogen atom, this would be the classical picture from the Rutherford model. We'd have the proton in the middle of the atom, positively charged, or rather from his point of view, this would have just been, of course, a nucleus with a positive charge. And then we would have had electrons orbiting around. And so here I'm just showing the case of the hydrogen atom, where we've just got one electron orbiting the proton. And so we've got mass m, radius r, radius of the orbit r, and the electron velocity v. And so what we could do, just by using classical physics, is just do a force balance and look at the attractive Coulomb force, the electrostatic attraction between the electron and the positively charged nucleus. And so we know the electron has charge of E, and the proton has charge of E as well. Obviously, the electron has the negative of the charge. And this is an attractive force, and so that basically compensates for the negative here. And we can set this attractive Coulomb force to be equal to the centripetal force. In other words, the force towards the center, which is basically changing that velocity vector here. This is the velocity. And that velocity vector is not changing in magnitude, but it's changing in direction as we get this circular motion around the nucleus. And so we just equate those two, and that would have been the model for the Rutherford model of the atom. Now, of course, there are problems with this. According to that simple model of an electron orbiting a positively charged nucleus, we could see that there's no restriction classically on the radius of the electron orbit. It could be positioned more or less anywhere relative to the nucleus, and so therefore also effectively have any arbitrary energy. And now also by classical physics, what we've got is a charged particle moving, and we have a moved, especially a circular motion in a charged particle, we should be seeing electromagnetic waves being emitted all the time from this accelerating electron. It's accelerating again because the velocity vector is changing due to the circular motion. So that's one issue. The second issue is that furthermore, given that it's given out this energy all the time, we'd expect something like this. We'd expect this electron to be basically falling in, collapsing towards the center, and ultimately colliding with the nucleus. I mean, this is a positively charged nucleus, this is a negatively charged electron, and because it's losing energy all the time with emission of electromagnetic radiation, we'd expect this collapse towards the center. So not a very promising model at all, somewhat catastrophic. The good news, though, is that this is not what is observed experimentally. Of course, we notice that most atoms are stable. But of course, this nonetheless is a big problem for the Rutherford model of the atom. And so therefore, we need to revisit classical physics when we get down to this kind of scale. And this is now going to open the way for considering what was done earlier on, prior to the Rutherford model, in considering what happens when objects in general emit electromagnetic radiation. So for example, a light bulb or a heated object, whatever it might be. we find that the work of Max Planck from years prior to the Rutherford model revealed the need already for something to change in classical physics. So let's take a look at that. What is it that we see being emitted from objects or from atoms? Well, the first observation, as I indicate on this slide, is that everything glows. Everything effectively has some kind of non-zero temperature, and as a result, there's electromagnetic radiation that is emitted from more or less every object, according, among other factors, to the temperature of the object. Now, this might seem counterintuitive. I mean, if you switch the lights off in a room, for example, you don't expect to see anything at all. So where is the electromagnetic radiation? Well, just to give you an obvious example, here we've got a kind of a night scene from a pilot in a plane, for example. And at night time, you might not see anything at all. But if you've got an infrared imaging camera, then suddenly you can see details very clearly indeed. And this is because there is infrared electromagnetic radiation being given off from the ground. And so this is again an example of how everything is indeed glowing. Everything is giving off electromagnetic radiation. It's just that a lot of it is not in the visible part of the spectrum. Of course, this is not to be confused with light reflections from objects. We're talking about lights off, what is being emitted from objects. And so typically it's not in the visible range. However, if you increase the temperature of objects, then of course we know full well that if you heat up a metal, for example, it becomes visible. We end up getting these kind of red, orange kind of colors showing up by the increase in temperature in the metal. Or if we go even further to welding, for example, we can even kind of get blue, white looking light coming off from these extremely hot objects. Even ultraviolet light is given off. So this is something that we do experience in practice. It's just that a lot of the time, well, all the time, we only really look at the visible part of the spectrum. So just a quick reminder as well of what the EM, the electromagnetic spectrum, looks like. This is the entirety of the spectrum that we know of, ranging from very large wavelength radio waves all the way up, all the way down rather, towards the atomic and nuclear scale, where we're dealing with kind of wavelengths corresponding to gamma ray radiation, or at the atomic level typically X-ray radiation. So we can see that for this range of wavelengths and for this range of frequencies, we also have associated with those wavelengths and frequencies of electromagnetic radiation this temperature indicator at the bottom, which is just saying that for objects, for example, around about 100 Kelvin, that's minus 173 degrees centigrade, you can still see here that we'd be getting electromagnetic radiation being given off in the kind of infrared region of the EM spectrum. So this kind of temperature bar at the bottom is just indicating that for objects of temperatures ranging from 1 Kelvin up to say 10 million Kelvin, we can see that we get a peak of emissions of electromagnetic radiation according to the object temperature. So that's just an aside, a reminder of the EM spectrum. I just want to focus again on the issues that were faced in classical physics in terms of describing this emission of electromagnetic radiation from objects of particular temperatures, because it was an issue and it was encountered in the context even of improving light bulbs, which of course are giving off electromagnetic radiation in the visible region. So to consider the problem, we need to talk about what's called black bodies. Now, it's called a black body because it's viewed as something that can perfectly absorb any incoming electromagnetic radiation, as well as emit perfectly electromagnetic radiation. And so a good example is what I'm showing on this slide, which is the sun, which is at the center of our solar system. To a very good approximation, that behaves like a black body. It absorbs the incoming radiation and can then also give off electromagnetic radiation according to its temperature. So this is kind of what's observed for this so-called black body radiation. What we're looking at here is the intensity of electromagnetic radiation being given off as a function of different frequency. Okay, so we've considered all the frequencies in that EM electromagnetic spectrum that we just looked at, and so you can look these up on that chart to have an idea of whether it's visible wavelength, whether it's infrared, ultraviolet. And this is showing us the typical spectrum for objects of particular temperatures. And I've highlighted here the case of the sun, as shown in the top right corner here, which is approximately 6,000 Kelvin at the surface. And so this indicates the kind of intensity of radiation, of electromagnetic radiation that is given off from the sun at that temperature at its surface. And then we could also look at it not just as a function of frequency, but we could also consider it as a function of wavelength as well. And so it's a very similar looking graph. We've just kind of reversed, or rather taken the reciprocal between the frequency and the wavelength. And so you could see these kind of spectral plots, in other words, the emission of electromagnetic radiation being as a function of frequency or as a function of wavelength. And so here again, we've got the sun giving off visible light, because that's the visible region there. That's around about 500 nanometers, for example, the visible wavelength. But you can see also it's giving off plenty of shorter wavelengths, in other words, much higher energy, higher frequency, as well as longer wavelengths, lower energy emissions as well. Anyway, the point is, these blackbody spectra were a big problem for classical physics. They couldn't actually come up with a theoretical model that describes these curves. I mean, these curves are in fact using what I'm about to show you presently, which is Planck's model. But without Planck's model, they couldn't theoretically derive these emission spectra from objects, from hot objects. So this was the classical physics situation. We had the so-called Rayleigh-Jeans law, which gives intensity of emitted electromagnetic radiation as a function of frequency and temperature. And you can see it's a function of the speed of light and Boltzmann's constant. But really, I just want to point you to the fact that it depends on the square of the frequency of the electromagnetic radiation, as well as being linearly dependent on the temperature T of the object. And so what we see with that rather shocking relationship here is that as frequency goes up, then obviously we square it, and that gives us the intensity. So this black line shows us the predictions of classical physics with the Rayleigh-Jeans law, that as we go to higher and higher frequencies, and so here I'm showing wavelengths, so that corresponds to going to smaller and smaller wavelengths, then the expected, or the modelled, using the Rayleigh-Jeans law, the modelled emissions of electromagnetic radiation get greater and greater and greater the shorter and shorter the wavelength. And of course, this is a far, far cry from what is required, which is these kind of curves here, where we have this virtually no radiation coming off at all for very short wavelengths, whereas Rayleigh-Jeans law is saying that it's approaching infinity. And so this was a huge problem for classical physics. You can see how badly this model fits the data. And that's why it was called the ultraviolet catastrophe, because these shorter wavelengths, so at the short end here, this is the visible part of the spectrum, around about 500 nanometers. As you go below that, you get to the ultraviolet region, very high energies. And you can see here that the Rayleigh-Jeans law was just way off in its prediction. In other words, the intensity should be reducing for those frequencies, those wavelengths, whereas Rayleigh-Jeans was saying that it was basically getting greater and greater. Hence the name catastrophe, because this was a huge issue with classical physics in terms of its predictions. So what was the fix? Well, this is where Max Planck, very famous now, of course, a Nobel Prize winner in 1918 for his discovery of quanta of energy, this is where he put forward a mathematical solution or a mathematical fix for this problem. And he didn't realize, I don't think at the time, that this was actually going to turn out to correspond to reality. And in fact, of course, it was Albert Einstein that used this very relation for explaining the photoelectric effect, which we saw in an earlier video. But anyway, Max Planck put forward this hypothesis, if you like, that energy comes in packets of size hf. Okay, F is the frequency of the light, of the electromagnetic radiation, and H is just a constant. Of course, it's called Planck's constant. But this has significant repercussions if we put forward a seemingly simple statement like that, to say that energy comes in these packets, these quanta. The point is that as we go to higher and higher frequency electromagnetic radiation, so the size, the amount of energy needed for each quantum, or each one of these quanta, goes up linearly with the frequency. So that means for high frequency electromagnetic radiation, there is a large packet of energy associated with what we now know as photons, these packets of energy. You need a lot of energy to create an ultraviolet photon compared to creating an infrared photon, for example. And this formula HF tells us the amount of energy needed to create a photon of a particular frequency. So this really explains what was going on. So at low frequencies, with, in other words, at the kind of redder end of the spectrum, F was small, the frequency was low, and so therefore the amount of energy needed for each one of those photons was relatively small. And in fact, you could almost say that you get a continuous kind of spectrum of energies. They just kind of come up, they get changed by very small increments, very small quantum, or quanta rather. Whereas when you get to higher energies, now the quantization is becoming more and more apparent, and we're needing more and more energy to generate a single photon of electromagnetic radiation. So this discretization effect becomes more significant at those higher energies, such as the ultraviolet. So using this, Planck was able to indeed generate curves like this. So these curves I've been showing you were in fact created using Planck's law, which is basically an upgrade on the Rayleigh-Jeans law, which was failing terribly, as we've seen. So with Planck's law, with the use of energy quanta, he ends up with this kind of spectrum here. And so that can be explained by the fact that as we go to shorter and shorter wavelengths, higher and higher frequencies, so we need more and more energy to create photons of that frequency. And so therefore, what happens is this doesn't carry on up to infinity. This rolls over and comes down, because obviously, as you approach zero wavelength, that's approaching near infinite frequency, which would require nearly infinite energy. So it's very obvious that these curves are going to come down and actually hit zero for zero wavelength, or if you like, infinite frequency, if such a thing existed. So we can understand how that quantization of energy, as Planck used, resolved that ultraviolet catastrophe that was present in the Rayleigh-Jeans law of classical physics. And so the Blackbody spectra, which, for example, match well with the sun, in other words, this matches well with the data, these spectra were beautifully produced by this Planck's law, which models those spectra very well indeed. And so there I'm showing explicitly that putting in the HF for the amount of energy needed for a photon, putting that into this formula here does exactly what I've just explained there. It just brings these curves down and stops them from shooting up to infinity, and again matches experimental data. So now we're in a position where we've seen that to explain blackbody radiation we need quantization of energy. Okay, that's how we explain experimental observation, whether it's with light bulbs, whether it's whatever object in the sky, or whatever object giving off EM radiation. We need Planck's law to accurately model what is going on, and the secret to that law is quantization of energy. So this was the missing ingredient in the Rutherford model of the atom, and so where we're going to go next is build in this known quantization of energy into the Rutherford model of the atom, and so therefore change it. And it was Niels Bohr who introduced that quantization of energy into the atomic model, and came out with some remarkable results that agreed beautifully with experiment. So I look forward to seeing you in the next video. Thank you.